Necessity is the mother of invention, and so it was with Santa Fe steam locomotive fleet. Each class had been designed for a specific purpose and for a specific geographic region. Continuing with this rule, Santa Fe designed the 5000 for moving fast freights on the Pecos division between Belen and Clovis, New Mexico. As plans for the 5000 began to take shape, Santa Fe assigned its prestigious 3800 Class 210-2s to earn their keep lugging freights over the Pecos division. The Pecos division's varied landscape of hills and flatlands posed interesting challenges to steam locomotive design, and Santa Fe experimented with different types. The railroad needed powerful and fast locomotives to travel the division's long distances. William F. Buck became superintendent of motive power on January 1, 1908, and soon he would begin investigating the technological possibilities of articulated locomotive design. Ever on the hunt for more powerful and efficient engines, William F. Buck thought that the advantages of articulated locomotives were what the Santa Fe needed for their challenging territory. The articulated design offered the power of two locomotives under the control of one crew, a very tempting economic advantage. The design promised high tractive efforts and the ability to negotiate sharp curves, which the Santa Fe had in abundance. There would be a high price to pay for these seeming advantages, however. Articulated engines use a single boiler to provide steam to operate two engines. This is accomplished by placing the rear, high-pressure engine under the rear of the boiler. It was rigidly attached to the underside of the boiler, firebox and cab, much like a non-articulated engine. The front low-pressure engine, however, is attached to the bottom of the boiler, with a pivot and sliding bearing arrangement, which allows the front engine to move side to side under the boiler as the engine goes through curves and turnouts. The distribution of the locomotive's weight on the drivers of articulated locomotives was never equal, since most of the weight was on the rear engine. This caused Malley and other articulated locomotives to be slippery on the front engine. The instability on the front engine kept top speeds down to 30 miles per hour or less, because going any faster caused frames and cylinder saddles to break. Some classes also experienced excessive back pressure buildup between the front and rear cylinder sets when run over 30 miles per hour. The first articulated built for Santa Fe was a 4462 Malley locomotive for passenger service of the 1398 class in 1909. Only 2 units were built, 1398 and 1399. Originally numbered 1300 and 1301, they were renumbered to make room for the 1927 class Pacific. The 1398 class 4462 engines had the following specifications: 24 by 38 by 28 cylinders, 73-inch drivers. Weight on drivers, 268,400. Total weight, 376,850. Boiler pressure, 220. Tractive effort, 58,000. The 1398 class had the same problem that the last articulated engines on the Santa Fe had: unstable front engines and high maintenance costs. The asymmetrical wheel arrangement made it impossible to get adequate adhesion on the front engine due to low weight on the drivers. This resulted in the front engine spinning wildly, while the rear engine had plenty of adhesion. This caused the receiver pipe between the high and low pressure engines to run out of steam and halt all forward motion. The railroad decided to cut the two 1398 class engines in half and build a pair of 462s that performed much better. Undaunted, after the 1398 class failure, the Santa Fe pressed on in their pursuit of the ultimate articulated locomotive. Many more experiments would be undertaken, including the accordion pleated boilers of the 1157, 1158, and 1170 class engines. These accordion flexible boiler locomotives only increased the nightmares of the Santa Fe's mechanical forces. 24 engines of the 3300 class 2662s were ordered and delivered in 1911. These engines had smokebox superheaters, and 4 of them had jointed boilers, which were believed to be improved design over previous ones. Both classes of Prairie Malleys were mounted on 69-inch drivers, and were the largest drivers to be applied to a 2662 before 1930. This was 15 years before 69-inch drivers were considered necessary for freight service. They received outside bearing radial trailing trucks, which was an innovation that was copied industry-wide. If the firemen could keep the Malleys' steam pressure up to their maximum 220 pounds, a near impossible task, they could trudge along with a 3,500-ton train at 20 miles per hour. This would translate into an average speed of 12 to 14 miles per hour between stations. The 69-inch drivers didn't work out on the Malleys because of the lack of stability on the front engines. They remained in freight service between Wellington and Clovis until they were retired in 1926 and replaced by the 4000 Class 282s. They spent their last days on the Kansas, Western Oklahoma, and West Texas branch lines, pulling harvest, wheat drags. Santa Fe had purchased a pair of 2882s in 1909. They were advertised as the largest locomotives in the world. The new locomotives, numbered 1700 and 1701, were renumbered in 1913 to 1798 and 1799. They were oil burners, equipped with the latest in modern appliances, including a Buck-Jacobs superheater and a Jacobs-Schubert firebox. These locomotives were known as the 1798 class after the renumbering. The 1798 Class 2882 engines had the following specifications: 26 by 38 by 34 cylinders, 63-inch drivers, weight on drivers 412,350, engine weight 462,450, boiler pressure 220, tractive effort 108,300. They were assigned to Tehachapi service and were somewhat successful, but they still suffered from the Malley instability problem. Santa Fe Mechanical Forces continued trying to solve the front instability problem, going so far as to adding a sandbox over the top of 1799's boiler, in the hope the added weight would help. They continued to have front stability problems as they worked out their service life in Tehachapi, until rebuilt under the direction of John Purcell's back to simple 282s at San Bernardino in January and February 1924. Both units were sold for scrap between 1950 and 1952. The experimentation with articulated locomotives reached its peak in 1911 with the design of the 210-10-2-3000 class. Built by the Santa Fe in 1911 at the Topeka shops, the 3000s had originally been envisioned for use as freight power between San Bernardino, California and Belen, New Mexico. They were created by combining the existing high-pressure 900 and 1600 class engines with 10 new low-pressure units purchased from the Baldwin Locomotive Works. The 3000 Class 210-10-2 engines had the following specifications: 28 by 38 by 32 cylinders, 57-inch drivers, weight on drivers 550,000, engine weight 616,000, boiler pressure 225, tractive effort 111,600. These locomotives were very powerful and were capable of pulling anything the dispatcher could come up with, but they were very slow, and with a total length of over 120 feet, they could not be turned on any Santa Fe turntable. Less than 6 years after the development of the 3000 class, they were all bisected and condensed back to simple 210-2s. As much as possible, all other classes of articulated engines were reduced back to simple, non-articulated locomotives. Those that couldn't be converted were sent to scrap. The Santa Fe Railway was done with articulated locomotives forever. However, during World War II, Under extreme need to be able to handle war traffic, they did purchase 8 Norfolk and Western 2882s for helper service on Raton. The Norfolk and Western Malleys were slow-speed compounds with a top speed of 20 miles per hour. Their Alco boilers were a good free steaming design, however, and Santa Fe even thought about using the design on the 3751 class engines. Dieselization prevented this. If the Santa Fe's articulated engines had been simple, instead of compound, they may have had a better experience. No matter what wheel arrangement they tried, the bad points of the articulated locomotives outweighed the good. The Santa Fe went on to develop other ways to provide high tractive effort and horsepower. Their new designs, which became the 5000 class, were far superior to any articulated locomotive. John Purcell stopped ordering Malleys and articulated engines soon after he became the head of the Santa Fe Mechanical Engineering Department. He rebuilt the 3000 class 210-10-2s to simple 210-2s in 1915, and allowed one final order of compound engines, the 3500 class Pacifics, in 1914. He trimmed the fleet of the 956 compound locomotives on the roster after 1915, and returned the 210-2 tandem compounds of the 900 and 1600 classes to simple. By 1927, he had also converted the 280s, 262s, 462s, and 442s. John Purcell believed that the ultimate steam locomotive design only had 2 cylinders, and he was right. The 3800 class duplex stoker allowed them to easily outperform the Malleys, which had to be fired by 2 firemen on long runs. While 3829 was under construction, Purcell requested the 4-wheel trailing truck be installed to experiment with the future possibility of increasing the firebox size. If successful, the 4-wheel truck design would pave the way for larger fireboxes and locomotives that were more powerful. The 3829's 4-wheel trailing truck provided the mechanical department with a wealth of in-service experience, and gave Santa Fe the supporting information it needed to pioneer the design into the 3751 class delivered in 1927. In 1930, steam pressure on the 3800s had been increased to 210 pounds, thereby increasing the tractive effort to 81,500 pounds. The 3800 class 210-2s proved very popular with company bean counters and trains crews alike. The 210-2 3800 class gave the railroad its first real taste of a high-powered locomotive, but exposed the weaknesses of a bolted frame compared to a cast design. These engines were good pulling machines, however, some of the earlier frames were subject to breakage from the high back thrust of the pistons because they were not a one-piece design. The 3800 class also provided practical knowledge of superheaters, feedwater heaters, boiler pressures over 200 pounds, and about 10 years experience with a 4-wheel trailing truck on number 3829. Purcell, having eliminated Malleys and compound locomotives, drastically reduced maintenance and crew costs. His 210-2s had increased system-wide speed and efficiency, and the Santa Fe had learned a lot about designing locomotives for the railroad's terrain and traffic demands. From the 210-0s, Santa Fe learned the value of high tractive effort and the pros and cons of tandem compound steam. Compounding steam gains high tractive effort but causes high maintenance costs. Then, Santa Fe learned the value of adding a 2-wheel trailing truck to guide a locomotive in reverse, which is especially useful in pusher and switching operations. Now it was time to combine all this knowledge into a state-of-the-art, high-speed, dual-purpose passenger/freight locomotive. The railroad wanted to blend the 210-2's reliable power with a larger firebox and boiler, thanks to a 4-wheel trailing truck, combined with 73-inch driving wheels, for good speedability, and 210 pounds of boiler pressure. All this would be built on a one-piece cast frame, for enhanced resistance to the back thrust of large pistons under high pressures. In 1926, Concurrently with the development of a new freight locomotive design, Purcell's mechanical department began creating an experimental 484, based on the 3700 class, 482 mountain type, relying on the experience gained with the 3829-210-4. Designed by Purcell, Charles T. Ripley, and H. Lanning, the new 3751 would have a one-piece engine bed, 30 by 30-inch cylinders, and 73-inch drivers. Charles T. Ripley was Santa Fe's chief mechanical engineer from 1922 until 1938. Ripley designed dynamometer car number 29 in 1911. This test car was used to test the performance of all Santa Fe steam and Pioneer diesels from 1911 to 1960. It was so successful that other railroads asked Santa Fe if they could use it to test their locomotives. H. Lanning was Santa Fe's mechanical engineer Topeka. Lanning and his staff were highly skilled in locomotive design engineering. Specifications for new locomotives were drawn up by his design team and forwarded to Baldwin for construction. Usually, a member of Lanning's staff would accompany the designs to Baldwin and supervise the construction firsthand. The 99 and 15/16 inch boiler operated at 210 pound steam pressure. The four-wheel trailing truck supported a large 108 square foot radial stay firebox, and the locomotive was coal-fired, with a duplex stoker. The total engine and tender weighed in at 704,900 pounds. The 3751 experiment went so well that 13 more units were ordered immediately after completing the tests. Purcell's satisfaction with the design results led him to incorporate the 3751's features into a 210-4 type design on 69-inch drivers. This new 210-4 would become known as Engine 5000, nicknamed the Madam Queen. Madam Queen was a character on a very popular radio program during the 1920s. Reportedly, one of the first engineers to operate the 5000 affectionately referred to it as Madam Queen, and from then on the locomotive was known only by that name. Purcell turned the actual design of the new 210-4 over to mechanical engineer H. Lanning and his staff in Topeka, Kansas. E. Chapman, engineer of tests, became involved just as he was in all locomotive development from 1927 forward. Purcell and Lanning's new 210-4 became class number 5000. Like the 3751, it would have a radial stayed boiler, but pressure would be increased to 300 pounds, which at the time was the highest steam pressure ever attempted in a conventional design. Other motive power departments did not universally accept this high pressure. Most railroads never bought any locomotive with pressures higher than 275. The 104-inch diameter boiler was the largest yet. 2 Nicholson thermic siphons were in the firebox, and 1 in the combustion chamber. Total heating surface was 9,665 square feet. The engine was given a Type E superheater, and Chapman-Lanning starting valves that admitted steam through a 1 1/4 inch pipe during expansion. This was considered necessary for good operation on an engine using 60% maximum cutoff. 2 8.5-inch cross-compound air compressors were mounted on the pilot deck, and the closed-type Alesco feedwater heater was mounted on the smoke box just behind the bell. This gave a very good-looking front-end appearance. Most other Santa Fe engines mounted Alesco feedwater heaters on the pilot deck. After number 5000, most engines were converted to the more efficient Worthington feedwater heaters, but the 5000 never received the Worthington conversion. Number 5000 had 2 sand domes with the same dimensions as the 3751 class. An external dry pipe, mounted on top of the boiler between the cab and the steam dome, provided superheated steam to the cab auxiliaries dynamo and stoker engine. No booster was ever applied to the 5000, because Purcell believed that boosters were not needed on high-speed freight engines. The tender was unique to the 5000, because it was designed with the locomotive. It carried 20,000 gallons of water, 27 tons of coal, and was given badge plate number 5000. When the 5000 was converted to oil in 1940, the tender's coal bin was removed, and a new oil tank was dropped into the space. The engine and tender finished out at 111 feet, 11 inches, with a wheelbase of 99 feet 5 inches, so there was no problem turning the 5000 on the 120-foot truss turntables at Clovis and Belen, New Mexico. In $1930, the locomotive's design and construction costs totaled $133,902.80. She was delivered in December 1930, and operated out of a pool of 20 3800s on the Pecos Division. Whenever a heavier than normal train showed up that needed to be moved fast, the 5000 usually answered the call. With a 20,000-gallon tender and 27 tons of coal, Madam Queen required only one water and coal stop on each district westbound plus an engine crew change stop at Vaughn, New Mexico, where the rods would be lubricated, and the sand domes topped off. On the eastbound trips from Belen, water and coal were loaded at Willard. Madam Queen received coal, water, sand, and lubrication service at Vaughn. If conditions were good, the engineer could make it to Clovis, without taking on additional water or coal. The 3800's smaller 15,000-gallon tender, and 20-ton coal capacity, required at least one additional stop in each district. The 5000 always steamed better, if it was worked at close cutoff, with full throttle. Santa Fe set about designing its 5000 Class II 10-4s, based on all its steam locomotive experiences gained system-wide, and particularly on the Pecos Division. The original design specifications in 1927 called for a 210-4 freight locomotive with 69-inch drivers, 325 pounds per square inch steam pressure, radial stayed firebox, with 121.5 square foot grade area, one-piece cast steel frame, with cylinders cast integral, Type E superheater, Elesco feed water heater and standard stoker. 5000 was supposed to be ready in early 1930. The one-piece cast steel frame, the largest single casting in the world at that time, was causing the design to go over the weight limit. Correcting this problem took considerable time, and Purcell, Ripley and Lanning worked closely with Baldwin personnel to get the engine's weight under control. While most of the weight problems stemmed from the massive one-piece frame, other adjustments had to be made to complete the needed weight reduction. Dropping the boiler pressure from 325 to 300 pounds allowed the 5000's frame to be lighter, without compromising the needed performance. It was a good thing in the long run that the 5000's steam pressure was reduced to 300, because even at 300 the 5001's and 5011's broke side rods due to the tremendous piston back thrust. In addition, a reduction in the 5000 sand domes would save even more weight. Ultimately, the 5000 received the same size sand domes as the 3751 class. These changes brought the 5000's weight down to an acceptable 502,600 pounds. Lanning's team was so skilled at the weight reduction engineering, that the final blueprint of the locomotive as built, shows that even after trimming off 5.2 tons, weight on the drivers was increased 11 tons. After spending 3 years in design, and 1 year in manufacturing, Santa Fe finally received number 5000 from the Baldwin Locomotive Works, on December 15, 1930. She was put into regular freight service on the Pecos Division on December 26, 1931. Test 87249, ordered in January, took place starting with Run 1 Clovis Belen on July 20 and 21, 1931 and concluded with Run 12 Belen-Clovis on August 6 and 7, 1931. Dynamometer Car 29 was the brainchild of Charles T. Ripley and T. E. Layden. Both men supervised the design and construction of the car, and all instruments. The car was created to measure and record the full spectrum of locomotive performance, while the locomotive was being used in actual freight service, under real-time load conditions. It was a true mobile laboratory, and was used to evaluate all Santa Fe motive power up until its retirement in the 1960s. Santa Fe Dynamometer Car 29, recorded drawbar pull, speed, rate of firing, rate at which water was supplied to the boiler, air brake operations, time of passing stations, and starting and stopping. Cab readings included boiler pressure, steam chest pressure, back pressure, position of the throttle and reverse gear and temperature of the smoke box gases. Crosby steam engine indicators were used to determine the steam distribution in the cylinders, and two 4-inch hot water meters were used, one on the suction line of the pump, and the other on the injector, to record the amount of water delivered by either, which was recorded on the chronograph chart. Check readings were also made by means of gauge boards on the tender. An electric contact was attached to the stoker conveyor, which recorded the revolutions. Temperatures were taken of the feedwater before entering and after leaving the feedwater heater. The amount of cinders thrown from the stack was determined by a catcher placed over the stack, covering about 1.95% of the area, diverting the cinders caught into a container. From the amount of cinders caught, the total amount discharged was determined. The coal consumption was determined by leveling the top of the tender at the beginning of a trip, filling to the same level at the end, and taking the weights shown by the coal chute scales. The test was made on the 1st and 2nd districts of the Pecos division between Clovis and Belen. The ruling grade is 0.6% westbound. Eastbound it is 1.25% from Belen to Mountain Air, and 0.6%. The runs established tonnage ratings for work on the Pecos division Clovis-Belen-Clovis. 5,000 was dispatched from Belen to find test results Belen Mountain Air over the eastbound 1.25% ruling grade and westbound from Clovis to find tonnage ratings on the 0.06% ruling grade between Clovis and Vaughan. Belen to Mountain Air was usually with 3800 class helper and train weight averaged circa 4,000 to 5,000 tons to Mountain Air, where the helper was taken off. Trains evidently moved without helper for the continued move to Clovis. On Run 10, she was operated without helper, Belen to Willard with 3,224 tons in 67 cars. We will be discussing Run 10, as it is the only test run without a helper, and gives us a clear indication of her abilities on the Pecos division that she was designed for. The locomotive was handled by pool crews, which changed at Vaughan going either direction. The road foreman of engines, or the fuel supervisor, accompanied all trips to assure uniform handling and full boiler pressure. Locomotive was operated with wide open throttle where conditions permitted. In preparing the locomotive for test, in addition to applying test apparatus, all driving wheels were dropped, lateral was taken up, and main floating bushing renewed. Run 10, Belen to Clovis, was on August 4 and 5, 1931. Crews were called for 12:30 p.m., and train departed at 1:15 p.m. This was a single-engine train, consisting of 3,224 tons in 67 cars as far as Willard, where the tonnage was increased to 4,157 in 76 loads and 4 empties. Stops were made for 1 minute at Belen Switch, at Shoal, 11 minutes, meeting number 21, Willard 35 minutes, taking coal, water, cleaning pan and picking up cars, and arrived at Vaughan at 6:18 p.m. Total trip time was 5 hours, 3 minutes, dead time 47 minutes, running time 4 hours, 16 minutes. The temperature dropped from 90 degrees Fahrenheit at Belen to 76 at Vaughan. It was clear and dry to Vaughan, where it rained for a short time, then cleared again. The lubrication was fair, except right piston was dry coming up to mountain air. Hitchcock sand spreaders were applied to number 1, number 2 and main drivers, making 3 sanders in forward motion. The flange oiler was kept operating and engine slipped several times entering curves. Boiler and feed water heater were washed at Albuquerque, and agitators were removed from feed water heater, which caused a drop of 16 degrees in temperature of water leaving the heater. An extension, 14 inches high, was placed over the stack, which improved the steaming qualities. The dead time at Vaughan amounted to 1 hour 35 minutes servicing engine and filling out to 6,014 tons in 114 loads. Train departed at 7:52 p.m., stopped at Joffre 29 minutes meeting number 33. Fort Sumner, 6 minutes water and meeting number 9, 16 minutes, entering Clovis Yard, due to heading in on wrong track, and couldn't back out. Total time 5 hours 12 minutes, dead time 50 minutes, running time 4 hours 22 minutes. The temperature was 70 degrees Fahrenheit, with a side wind of 15 miles per hour. The coal contained considerable moisture due to recent rains. 22 pints of valve oil were consumed on the trip, making approximately 11 miles per pint. The locomotive steamed very well with a strong draft, which incurred a stack loss of from 12 to 14% of the coal fired. The amount of cinders discharged relieved the ash pan condition, which frequently filled up to the point where there was danger of burning out the grates. The locomotive had an extraordinary capacity for sustained power at high speeds, which is reflected by power performance curves. It exerted a drawbar pull of 50,000 pounds at 33 miles per hour, equivalent to 4,350 drawbar horsepower, at which it had a machine efficiency of 84%. With a drawbar pull of 82,500 pounds at 15 miles per hour, the machine efficiency was 90.0%. Purcell was obviously pleased with her performance, as this letter dated September 13, 1931 to H. Lanning indicates that Purcell would ask for additional funding from Vice President Wells to purchase more of the 5000 class in 1932. The 5000 ran more than 1,750,000 miles in her career on the Pecos Division, and occasionally helped the Super Chief up Raton Pass. In the 1930s, the 5000 helped pull the country out of the Great Depression. During World War II, Madam Queen was run day and night moving freight and troops across the country. After the war, and into the 1950s, the 5000 was used as an experimental test bed to try out new appliances, or mechanical experiments. Modern diesel technology has not surpassed the 5000's tremendous horsepower without using multiple units. After hauling the nation's heaviest freight trains at a fast pace for 23 years, Madam Queen was retired in November 1953. Fortunately, the railroad did not scrap the one-of-a-kind locomotive, but rather donated it to the city of Amarillo. Number 5000 was placed on static display in front of the Santa Fe Depot on April 17, 1957. The Railroad Artifact Preservation Society spearheaded the relocation under the leadership of Society President Sam D. Teague. In order to cosmetically restore the locomotive, it had to be relocated to a new site 4 blocks away from the depot site. The relocation of 5000 was featured on the History Channel Mega Movers series in May of 2006.